Hello everyone, this is Analog Circuit Design, Lecture 18, Differential Amplifier, Part 1. I would like to my advisor Michael Flynn for the lecture note and then also Seung-Jong Lee for the review. First, motivation. Before starting, let's see what differential pair is. So differential signal is measured between two nodes. It can be current or voltage. Both of them are fine. That have equal and opposite phase signal. So let's see this figure. The left one is single-ended. So single-ended means that the output, this node has this will signal, and then the reference would be the ground. So only a single node has a signal, but in a differential signal here, you see that the output would be the voltage between this X node and Y node. And then output X node also has a signal, and then Y also has a signal. So unlike here, so here V out is voltage between this node and this node, and then this node is ground. So only single node is moving, but in differential signal, both nodes move. And then the other thing, the important part is that this one has equal amplitude and opposite phase. So you see that they're opposite. So in a time scale, the signal will be like, if this is voltage X and the voltage Y will be like this. And common mode level, this is a important terminology. The common mode means their DC voltage. So here in this case, this. So basically this differential pair is really important. It's like you can see it in every analog circuit, so essential for analog circuit design. Then why do we need this? Why are we interested in differential pair? What's the motivation? The first one is higher immunity to environmental noise. It means that rejects common mode noise. So this is important term, common mode noise. So for example, in this figure, let's say we have a common source amplifier, and then we have the output here, Vx. But in the real chip, in the layout, there's other like interference circuit, like aggressor, can aside in the near to this signal. So in the real chip, between these two lines, there's a parasitic capacitance. Parasitic capacitance means that they are kind of connected electronically. So for example, let's say there's some clock signal, like as an interference. If this clock toggles, then because of this parasitic capacitance between these two lines, it gives them this kind of noise, picking. And this picking is not good, of course, right? It's like a noise interference. But let's assume that if we use a differential pair, and if we draw a line like this, so in the layout, let's say the metal wire, the routing is actually looks like this. So we have Vx and Vy, and then let's say V out is Vx minus Vy. And there's this clock wire, which is not, which is an interference. So same, if clock toggles, because there is a same space, each L2 and then L3, which means Vx and Vy experience the same noise. But in this case, the direction of the noise are the same. So if we just subtract them, this will give us a like clean sine wave, because this noise these noises are common. So the common noise can be subtracted. So that's why we can say the differential pair is good, because it can reject common mode noise. So we can also reject supply noise. Well, supply noise is common mode noise. So if you see this circuit, if the VDD has noise, then this noise will go directly to Vout. And the VDD is usually not clean, it's noisy. So in like a real chip, and in like maybe like phone or some modem, the supply is generated by something like PMIC circuit, like PMIC circuit. So it means power management IC, which is chip, and those are usually like noisy. For example, this can be let's say like buck converter. So buck converter is switching power, so it generates like, let's say like 1.2 volts, or maybe LDO. So LDO is like cleaner version of the power generating source, but anyway, this power is generated by some PMIC, and then they are noisy. Also, there's the other reason that the power is noisy. So usually there's the other circuits. So there's lots of circuits, and even maybe other chip, IC1, maybe IC2. So like different circuit, different chip shares the same power. That happens. So, and this chip also consumes a lot of current, right? Current. And then this current is not clean. This current may be really like jiggly. So these can go be a noise to the VDD too. So this is a like a can be a huge thing if we don't cancel it. But in single-ended circuit, we cannot cancel this VDD noise. But if you use a differential circuit, in differential circuit, the Vout is Vx minus Vy, right? But Vx will be the Vx like signal plus V noise, and Vy also Vy signal plus V noise. And if we subtract them, the Vn is common, V noise is common, so we can cancel it. So that's why this common mode noise from the supply through this Vx and Vy can be cancelled if we subtract them. So it means that the differential pair has good PSRR. PSRR means power supply rejection ratio. So the definition is here. It just means that if we put some noise to the supply, then how much fluctuation we're gonna see at the output. If PSRR is really good, which means if PSRR is really low, that means no matter how much we fluctuate the VDD, the output will stay still clean. So as I said, supplies are really dirty in real system. And this is the other reason. So far here there was a rejecting common mode noise, and the other good part of the differential pair is good for linearity. Like this HD2 means harmonic distortion 2. Those can be cancelled if you use differential pair. So we talked about what the differential pair is, and then why differential pair is useful. Well, actually differential pair is essential. I mean, we must use differential pair most of the case. And then let's see the basics of differential pair. First, we can think of very simple differential circuit, which is just duplicate two single-ended circuit. For example, this single pair, this is what is it? This is common source amplifier, right? But this is single-ended. So one way, the simplest way we can make a differential circuit is just place two of them together, and then let's say we assume that we have a two differential input. Then each output can be a differential output. So again, the V out, the overall V out would be V out 1 minus V out 2, right? So this is actually a differential circuit, but it has a problem. The problem is that the variation of the transconductance leads to a change in the small signal gain. It means that the variation of the small transconductance is like a variation of the current. So let's see this graph, this waveform. So let's say V in Cm is placed in the right value, and then V in 1 signal is like this, and then V in 2 is in the opposite phase, so that's a differential input signal. And then with this, we will expecting this V out 1 and V out 2. They're also in like 180-degree phase difference, while the amplitude are equal, right? And then we do have this V out Cm common mode. But the problem happens that if the input common mode changes, so let's say this is good one. This is what we desire to operate, but assuming that input common mode is somehow lower than this. So if input common mode is low, that means the V out will increase, right? Because if input common mode is low, then the current decrease. And then the V out common mode is RD minus ID, right? So as I said, again, so V out Cm is VDD minus RD ID, where ID is COX, WOL, and then VCM in minus VTH. Let me write it down again, where ID is COX, W over L, W over L, and then V in Cm minus VTH. Assuming that just ignore the channel length modulation. So as we can see, this current ID is when input is V in Cm. So if input is V in Cm, so that's the ID, and then the V out Cm will be a function of V in Cm, right? So if V in Cm changes, then V out Cm also changes. In this case, V in Cm decreases, which means the current decreases. That means the V out Cm will increase, right? The problem is if that happens, the V out Cm can be too high, and then maybe our output can be clamped to VDD because it can't go further. And also, the current change will change the GM, and then the gain will be different. So this is not good because there can be some error in common mode voltage, and we want something better because this circuit is too sensitive to the V in common mode. So that means we need a well-defined bias currents. So these things happens because the bias current ID changes depends on the V in Cm. Okay. So it also means that we want bias current, like independent of V in Cm. That's what we want. So we can, because of the previous issue, what we can do is we put a current source here. It's like a set the current ISS here to make ID1 plus ID2 independent of V in Cm. So in the previous slide, the circuit was this one, right? Just simply put two circuits here. And then the problem is the problem with this circuit is that IDCM, which is when V in 1 and V in 2, so IDCM is like 1/2 mu n COX W/L V in Cm minus VTH squared. Okay. So the problem is that IDCM is sensitive to V in Cm. So it will cause first V out Cm is sensitive to V in Cm, right? Because if current changes, then because of the common mode, V out also changes, right? Here. And then the other problem is Gm is sensitive to V in Cm. That means gain changes. That's not good, right? We want gain a constant. So to do this, the good thing is that ID1 plus ID2 is independent of V in Cm. Of course, this is when ignoring channel length modulation. It's because usually this current source will be replaced like this, VB and like this. So if there's no channel length modulation, the current of this MOSFET is always ISS. So this two ID1 and ID2, the summation of it is independent of V in Cm. Even if we consider like channel length modulation, still we can kind of keep the same keep the summation of these two current as a ISS. And also, so if the current is the same, then we can keep V out Cm as a constant regard independent of V in Cm. So that's because if our V in 1 and V in 2 are the same, then the currents are the same, right? Which means it should be ISS over 2 because they have to share the current, right? So here's the ID1 and here's the ID2, right? So VLCM is VDD minus RD here, RD, assuming that RD1, RD2, RD. I mean, of course. And then this current times ISS over 2, right? Again, this value is a large signal current. So now VCM out is independent of V in Cm. So now it becomes independent independent of V in CM. You may wonder why do we want this VCM out independent of V in CM? Because usually this output will go to some other circuit, right? And then that other circuit requires some specific input level. So that's why we want to keep this as a constant. If this changes, then our following circuit will be in trouble. Let's see how it works. So as I said, the differential pair, the input always operate as a opposite phase. So it's good to say V in diff is V in 1 minus V in 2, right? And then if V in up works like this is V in, then always V in 2, so that will be V in 1. They're in opposite phase and then equal amplitude. So that's V in, and then first let's see how the V out changes, V out 1 and V out 2. So here first, if V in is, let's see the far right side, the extreme case. If V in is a lot larger than V in 2. If this is a lot larger, then what happens is the current will flow all the way here. So this MOSFET will not flow anything, and then all currents will flow here. So then what happened to V out 1? V out 1 would be VDD minus, because current will flow here, ISS. So V out 1 will be VDD minus ISS RD1, right? And that's the point here. And that's a point here. So this one is VDD RD minus VDD minus RD ISS, right? So that's here. And what happened to V out 2? So since there's no current flows here, V out 2 will be VDD, right? So this will be VDD. The opposite case, same, right? If at this point, V in 2 is larger than V in 1, which means that all the current flow here to V in 2. All the flow flows to this way, and then no current flow here. So V out 1 will be, since there's no current, it's VDD, right? V out 1 will be VDD. So I go here. V out 1 will be VDD. V out 2, since all the current flow here, so the voltage will be VDD minus RD ISS. These things happen because the sum of these two currents, as we said in the previous slide, ID1 plus ID2 is ISS. So that's why these things happen. And also because if V in is large, that means larger VGS. And then the current of this M1 is defined as, VGS1 minus VTH squared times like 1 over 2 mu and COX. So that's why if the voltage here is large, then because of the large VGS1, current becomes larger. This graph is the same graph, basically same graph, but the y-axis changes to V out 1 minus V out 2. So at the very end here, V out 1, at this point, V out 1, V out 2 is at VDD minus the ISS, right? So that will be RDISS. The opposite side, the different polarity. And you can notice that if the input, so we assume that this is V in. So this is V in diff, right? as we said here, V in diff is V in 1 minus V in 2. So if V in diff is positive, what do you see? The V out becomes negative. So its polarity is negative. And that makes sense, right? So because 1/2 part is common source amplifier, and the common source amplifier polarity is negative because the common source amplifier gain was minus GMRD. So we'll come back to the gain later, but interestingly, the differential pair gain is also represented as minus GMRD. But we'll get back to that later. And there's the other thing that we can look into as a V out CM. V out CM means when there's no difference between V in 1 and V in 2. If V in 1 and V in 2 are the same, then that's the voltage when V out CM happens. And you see that there, if this V in 2 and V in 1 are the same, then the current will flow half, right? So that's why VDD minus RD times IS over 2. That's V out CM. And as we discussed, is this dependent on the V in CM? No. So that's a good part of this current source-based differential pair, that this is independent from V in CM. That's a good part. So far we discussed about the motivation of differential pair and then basics of differential pair. And now let's look into more detail with some quantitative using equations. The goal of this large signal analysis, so we want to look for V out is a function of V in, where V out is V out 1 minus V out 2, while the V in is V in 1 minus V in 2. If you see a little further the circuit, first assume lambda is 0, which is we're going to ignore the channel length modulation. V out 1 is VDD minus ID1 RD1, right? Because we're looking at large signal model. And V out 2 is VDD minus ID2 RD2. And then let's say RD1 and RD2 are the same. So we see there's ID1 and ID2, right? So it turns out we need ID1 minus ID2 as a function of V in 1 minus V in 2. So this is what we're going to proceed for our large signal equation. So it means from here we're going to look at the current out. I brought this paragraph from Razabi book. It shows what it says, what we discussed in the previous slide, that V out 1 minus V out 2 is a function of ID1, ID2 minus ID1. So here, well, this part, and since VP is V in 1 minus VGS1, right? Because here is VGS1. And VP is also V in 2 minus VGS2. So this gives this. So we're going to use it. So we're going to do some further calculation. So here, this paragraph is from Razabi, chapter 4.2.2. For the square law, we can change this, right? And therefore, VG just root at the right side and the both side, and then move it to the right hand, and then we'll got this. So in previous slide, what we got was Vn1 minus Vn2 was VGS1 minus VGS2, right? So by using that, we got this. So Vn1 minus Vn2 is VGS1 minus VGS2. So this VTH will be removed, assuming that they are in perfect match. There's no mismatch. Then we got this equation. And as we said, our target is we want to calculate the differential output current ID1 minus ID2, right? This is our goal. So scaling these two sides of 4.5 and then recognizing that ID1 plus ID2 is ISS, then we got this equation, and then just make it clean. Then we got this. Let's do further. Let's go further. This 4.7 equation is from the previous slide, and then if we use this relation and substitute it and do something, and then we got this finally. Okay, so let's focus on this equation, which is 4.9. So let's see this equation. And if we draw a graph by using this 4.9 equation, then we got this graph. And then our circuit was this, right? ISS, and here's ID1, and well, here's ID2, M1, M2, right? So let's see this part. So see this part. If the Vin minus Vin2 increases, then the value, this differential difference between ID1 and ID2 increases, right? It means that if Vin increases, then ID1 increases, right? So it makes sense. This part also, if it goes negative, that means Vin2 increases. That means if Vin2 increases, so here's Vn1 and here's Vn2. So Vn2 increases, then ID2 increases, right? Then ID2 increases. So that's why ID1 minus ID2 will go negative. So this part is okay. But how about this part? It says that if you increase Vn more, then suddenly ID1 decreases, which doesn't make sense. So we're not, this part we'll ignore this, okay? This part we're not going to take this. And then let's see why this equation breaks at these 2 points. So we'll see why this part doesn't make sense, and then we can define this Vin peak here. So let's see how it works. First, as we discussed in the previous slide, this part, physically currents cannot fall off, so it's not true. It doesn't make sense. It doesn't make sense because what we're looking at the circuit is this. Note that we're looking at large signal model. And Vn1 and Vn2. So if we go to this way, that means Vn is a lot larger than Vn2. What happens is, if this becomes too large, then current will just flow here. So there's no current in M2, and only M1 will flow the current. So because ID1 plus ID2 is ISS, so it's just saturate. And we can, and but we got an equation in previous slide, right? We got the previous slide, the equation, and why this equation cannot predict this part. Because the assumption of this equation is M1 and M2 are in saturation. But after this thing happens, M1 and M2 are not in, for here, M2 is not in saturation anymore. Here, M1 is not in saturation anymore. So that's why this equation, well, we just substitute this Vin minus Vin2, this, because this equation is only correct for both saturation region, which is not true. So that's why this equation isn't working for this region. So only for M1, M2 sat region. Only works. I'll say only correct. Only correct for M1 and M2 in saturation region. So for this part, as I said, only M1 flows whole ISS, or this part only M2 flows whole ISS. So we can also calculate this V in pig easily, right? So that will be here. So this value can, if we substitute this value to here, then we got 1 minus ID2 is ISS. That's how we got this value. So if this value goes here, then we got this value. So within the range between minus delta V in peak and plus delta V in peak, which value is here, then the equation will satisfy this. But this part again, these region, for this region, M2 is off. So here's M2 off, and here M1 off. So that's why this equation is not correct for these regions. Again, so we got this, and then this is not true. And we calculate this V in peak in the previous slide as this. But interestingly, we can also represent this value, V in peak, which is the maximum allowed differential voltage, V in voltage, as function of this. So what is it is M1, M2, and SS, and assuming that they flow the same current when V in minus V in 2 is 0. If that's the case, ID1 is ISS over 2, which is 1 over 2 mu n COX W over L minus VGS1 minus VTH square. So this VGS is this. So it turns out square root 2 times V over drive in equilibrium. So our maximum input range of here is the square root 2 times V over drive in equilibrium. Also, we can calculate small signal gain from our large signal analysis. So let's look at this equation again, and this is delta V in, and this is delta ID. So if we do a derivative, then we got this value, and if we put delta V in is 0, then we got and this is actually GM. This is actually GM1 or 2 when V in is 0, which means V in 1 is V in 2. So our gain is, our effective transconductance is, this is GM at equilibrium. And when V in is, when the voltage difference is 0, then we got the largest transconductance. Next is small signal analysis for differential pair. First method for small signal model is superposition. What it does is we put V in 1, but ground V in 2. So we will only calculate V in 1 first, and then calculate V in 2 again. So for V in 1, we would like to see this part first, Vx. So if you change this circuit, and it becomes like this. So we want to get Vx over V in 1, which is here, and then this is a source degeneration, and then it can simply be this. Of course, we will going to ignore channel length modulation. So V in here to Vx gain is this. Next is we want to find the gain from V in 1 to V out 2, right? And then if you use a Thevenin equivalent, we can change it to here. And then Vt is same as V in. So Vt is V in 1. And this is common gate amplifier, and then we got this gain. If we change V in here, then we will get, we can change the V out, Vy by this. So we got these two equations, and what we want is Vx minus Vy, V in 1, and that will be minus Rd, 2Rd, and 1 over Gm1 plus 1 over Gm2. Assume Gm1 is Gm2, then it becomes Vx minus Vy over V in 1 is minus Gm Rd. If we rewrite, this becomes Vx minus Vy is minus Gm Rd V in 1. But what we have, another one is Vx minus Vy, let's say from V in 2. This is also the same, right? So that's where we use superposition. Let's rewrite it. So Vx minus Vy from V in 1 is minus Gm Rd V in 1. Again, what we are doing now is using superposition. Here's V in 1 and ground. So we do a superposition between this and ground and V in 2. So those superposition. So by merging these two equations, Vx minus Vy, sum of V in 1 and V in 2 is minus Gm Rd V in 1 minus V in 2. And this is actually V out, right? So it turns out V out 1 minus V out 2 divided by V in 1 minus V in 2 is minus Gm Rd. So that's our answer. The method 2 for small signal analysis is using half circuit. The lemma is considered a symmetric circuit. So this is important part, symmetric circuit shown in figure 4.28 here, where D1 and D2 represent any 3-terminal active device. So it can be MOSFET too. And suppose V in 1 and V in 2 change differentially like this, then the VP does not change. So that's what they're saying is if V in 1 and V in 2 change differentially, which means with a different polarity and equal magnitude, then this VP will not change. So what we can do is this can be since here becomes AC ground in small signal model, we can just change it like this, on in RD1. So gain would be minus GMRD. So we can get easily by using this lemma. Next, let's see the common mode response. For this differential common mode common source amplifier, VNCM has we need to set VNCM in certain range. We cannot put VNCM in any voltage. Again, what was the advantage of this? So this is basically that's this ISS, right? And we replace this ideal current source as this M3 NMOS current source. And then we also discussed in the previous slide that the advantage of using this current source, tail current source, is that we can operate the circuit kind of independent of VNCM. So it means that this circuit is independent from VNCM, right? And then the VNCM, just to remind you, the VNCM is here. So this is VNCM, and the input like V1 and the output. I mean the input V1, V2, V2 and V1, right? So the VNCM is the average value, the common mode voltage. So the advantage of this circuit is that the property is kind of independent from VNCM, but it doesn't mean that we can put VNCM in any value. We need to put VNCM in certain proper range. That's what we're gonna see in this slide. So the target of this slide, the goal of this slide is proper range of VNCM. Let's see this first. So x-axis is VNCM and the y-axis is ID1 and ID2. ID1 is the current flows to M1 and ID2 is current flow through M2, right? So let's think about at 0 voltage. What if we put VNCM 0 voltage? Then this NMOS will not turn on, right? Which means there's no current, and this P will go 0. Because this VB is not 0, right? We need to set this VB at certain point to set ISS. So this ISS is and this would be 3, and then VB minus VTH square. We're ignoring the channel length modulation. So if this V in CM is 0, but this NMOS try to flow the current, so VP will go 0. So that's why, like here, VP, if V in CM is 0, then VP is 0, right? So, but if we let's increase V in CM from 0 to a higher voltage, assuming the V in CM becomes larger than VTH1 at the very beginning, because at this very beginning part, VP is 0, so only if V in CM is larger than VTH1, then current starts to flow. So here, VP, so here once the V in CM becomes larger than VTH1, then current will increase, right? And current will increase, that means that V out 1 and then V out 2 before VTH1, since here M1, M2 off. That means no current flows here, right? Because we're not using ideal current source. At this point, we are using some NMOS current source. So the current will not flow when V in CM is too low. So the voltage of the out 1 and out 2 is VDD, right? And once the V in CM is larger than VTH1, then the NMOS starts to turn on, and the current flows, and it goes up. And then, of course, if current flow starts to flow, then V out 2 and V out 1 and V out 2 will decrease, right? And if we increase V in CM high enough, then the current at here, it becomes this ISS. So at this point, this will be ISS over 2, right? Because once these V in CM are fully turned on because of this M3, which is operated as a current source, 1 over 2, ISS over 2 will flow equally. And we need to know when is that timing. So this voltage means something that makes M3 saturation. So once M3 becomes saturated, then this will flow ISS. So here, once M3 is in saturation, then ID3 will be ISS, which is our target. And that voltage is here. So first of all, VGS3 is here, right? VGS3 minus VTH3. So to make M3 in saturation, we need VP should be larger than VGS3 minus VTH3, right? So that part corresponds to here. Then what about this VGS1? So VGS1 technically, it means that so VGS1 is VTH square 1 over 2 mu n COX WL, and this would be what? This ISS over 2. So that's what this VGS1 mean here. So this VGS1 at this graph means this one. So once VGS1 is high enough, then this transistor can flow whole ISS in saturation region. So so this VP is larger than this, right? So the minimum of the VP is this one, and plus VGS1. VGS1 is from VP to here. So once the VC in CM is larger than this, then the 3 MOSFET will be operates properly. So after this, current will settles at ISS over 2. And then here is 2. Here the voltage also, when the VNCM becomes larger than this, then the common mode voltage will be this. And this is important part. Tail voltage tracks V input CM. So tail voltage means VP. So tail voltage means VP. So you may wonder if what happens if we increase VNCM further, then will VGS increase too much? That means the current flow through M1 should be increasing. So that's not true, because if VNCM increases further, then VP increases further. VP also increases, so it's like VP will follow VNCM here. That's because, so here that tracks it, and it's because we ignore channel length modulation. So if we ignore channel length modulation, the current of this MOSFET is irrelevant from VP. So the VP will just follow VNCM. So if VNCM follows VP, that means this will keep VGS1 or 2 constant. So that's what happens. So in this slide, what we can get is V in CM should be larger than that value, VGS1, 3. So we got this one. Then what about here? So now let's see the maximum value of V in CM. So in the previous slide, what we got was V in CM should be larger than this is what we got from the previous slide, right? To make this M3 in saturation. So assuming that we increase VNCM too much, then what happens is if we increase VNCM too much, then M1 and M2 will be in linear region. But our assumption is that when we want to operate this circuit, M1, 2, 3 must be in saturation. That's the condition we want that. So it turns out the maximum will be the minimum value between VDD minus RD, this, plus VTH, or VDD. So let's see what it means. If this value is too low, then as I said, if V out is too low, then M1 will be in linear region, right? Because the saturation condition is VGS, the saturation condition, just a reminder, VGS minus VTH should be smaller than VDS. That's the saturation condition, right? So this condition comes from first one here, VDD minus RD ISS over 2. This will happen all the time because I mean, this is like a when there's no VIN, when this is okay, let me say this is V out CM, right? This is V out CM when VIN1 equal VIN2. So there's no difference then in the VIN CM. And this is the output CM, right? But in this case, this would be VD. So we can say VG minus VTH. So this is also what we can get to be in saturation region. Vg is V in Cm by VTH, and Vd is always this actually, right? Because because of this current source. This current source flows ISS, and that's why the one ISS over 2 will always flow here. So that's why this is VD. So it gives us that V in Cm should be smaller than VDD minus RD 2 plus VTH. That's why we got this at here. Then why do we use this mean value? Because sometimes this can be larger than VDD. If this is larger than VDD, then, well, we cannot make Vin larger than VDD, right? So that's why we just pick smaller value between 2. Next is common mode gain. The definition of common mode gain is here. Gain from common mode input to common mode output. So it means that common mode input is V in Cm, and common mode output would be V out Cm. So V in Cm is here, and then input would be V in 1 and V in 2, right? This is same for V out Cm. V out Cm also has its common mode. It's common mode, and then V out 1 will be like this, and then V out 2 will be like this. The opposite phase and then same amplitude. So what it says is, what happens if we change V in Cm? If we change V in Cm, then what happened to V out Cm? So ideally, we don't want them to change, right? Because as I said, after this amplifier, this V out 1 and V out 2 will go to the other amplifier. And then, and then the voltage of V out Cm is like a required from the next following stage. So we don't want to change. We don't want to change V out Cm. So it means that we want to keep V out Cm, want V out Cm constant regardless of V in Cm. That's what we want, and also that's why we use this current source, right? So for ideal ISS, the voltage gain for Cm, the common mode gain, which is V in Cm, delta V in Cm over delta V out Cm, right, is 0. First of all, ideal ISS, what does it mean? Ideal ISS means there's no channel length modulation. It means that ISS is only a function of VB minus VTH 3 squared. So the current will not change. If that happens, V out Cm is what? VDD minus RD ISS over 2, right? Because if this is ideal current source, always ISS will flow here, and that means ISS over 2 will flow. So that's why here. So this will never change, which means there's no change in delta V out Cm, so the gain is 0. And this is good. This is what we want. But of course, that's not the case in real life, right? This is not ideal. This is not ideal. Because why? Channel length modulation. Channel length modulation. So that's not ideal. That means there is output resistance. The output resistance of the current source, ideal current source, is infinite, right? But since our current source is not ideal, we do have output resistance, finite output resistance. So what we can do is we can use a Norton, right? Norton equivalent. So that will be RSS, assume, and then this is ISS. So this is what we can write. If that's the case, then common mode gain is not 0 anymore. As the common mode gain becomes larger than 0 due to finite RSS, which is the output resistance of M3. And let's see more in equation point of view, that how this RSS can impact our common mode gain. So as we discussed before, this can be replaced as RSS and ISS, right? And assuming that symmetric amplifier, because this is symmetric, like let's say there's no mismatch, everything is the same, then what we can do is we can like split them. So if we split them, it will be, this is M1, and this part is important. It will be R2 RSS, and here is V in common mode, and then this will be V out common mode, right? So the reason why we multiply 2 is if we merge two of them, then there will be two parallel to RSS. So what I'm saying is, if you merge them, that it will be like this, right? Because there's two of them. So this is parallel connection. It will turns out equivalent to RSS. That's why we multiply 2 here. And if we calculate the gain of it, this is a degenerated RSS. I mean, common source amplifier, degenerated common source amplifier. So the current gain will be V out, and the voltage gain will be V out CM, and then V in CM. And this is minus GMRD and 1 plus GM to RSS. So that's why we want to make this RSS large. Make RSS large to make AVCM goes to 0, right? That's why we need a large RSS, and then we can see in this equation that if we increase RSS, then this gain will go to 0. And here's some example that how the common mode gain can be a problem. So first, assuming that we do have these two amplifiers connected in series. So there will be V in 1, and then this will be V in 2. So assume the common mode gain of A is larger than 0. That means if we change v in, that means v in cm delta will make delta v ab cm, right? So ab is here. But actually it's okay, because int amp b will that delta VAB CM a big problem? So it's not really, because this so usually this common mode gain is not that big. So in this amplifier B, so let's say this is common mode A. So this amplifier B will this will cause delta V out CM, right? So our final signal is V out 1 minus V out 2. So in terms of output, this common mode change is okay. They are not seen at the output. So does it mean that the common mode gain is fine? Should we really care about this common mode gain? Well, in reality, we have to, but in reality, there's no perfect symmetry. So circuit is unsymmetric. So that's a problem. So in reality, the circuit is unsymmetric. That means if we have a common mode gain, that can become a differential mode input. So this means that common mode gain will transfer to differential mode gain. Right? Because of the unsymmetric. Now, if this is the case, then common mode gain will be a problem. So in this case, AVCM will be an issue. So with the unsymmetric, and that's the case in real circuit, this common mode gain will be a problem, because the common mode gain will converts to differential mode gain because of the unsymmetric. And if that's the case, when we see the V out, this common mode gain will impact our V out. So long story in short, we have to consider how to reduce the common mode gain, which means we have to make this current source good. Now let's see how common mode gain it will be converted to differential mode gain if we have a mismatch in differential pair. First case, assuming that there's a mismatch between RD and then RD plus delta RD. So this delta RD will be a mismatch. In this case, gain on each side now are different. So V out 1 gain is not equal to V out 2 gain. And we calculate the effective GM, right, on each side. What we did was like divide it by 2, split it, and then we put a 2 RSS, right? So with given that, the effective GM on each side is GM 1 plus 2 GM RSS. Of course, the GM can be either 1 or 2, right? So it means that to this side, the GM is GM1, 1 plus GM1 2 RSS. But in this case, we say that the GM is same. So, and also, oh, this side, this is also 1 plus GM or 2 RS. So their effective GM are the same here. Okay. Yeah, so the effective GM of each side are the same now because we assume that there's no mismatch in GM. So if V in CM changes, so it means that like common mode change. Let's see what happens. First, VX star, the GM, RD, and this. So it's because the gain is in CM and VX, right? And then this is effective GM times RD. And that's how we got this one. Right, so if we put these things to move here, then we got this one. Similarly, delta y, Vy is the same, right? This would be V in CM, GM 1 plus 2, GM RSS. But here we see the difference, RD plus delta RD. If we subtract them, then the difference would be delta Vx minus delta Vy, right? This is delta V out CM, right? And this would be delta V in CM, GM 1 plus 2 GM RSS, delta RD. So as a conclusion, AV CM to DM. It means a common mode to differential gain would be GM1 plus GM2 RSS times delta RD. So we can see that if you have a resistor, the load resistor mismatch, that will convert the common mode change to the output change. So it means that delta V in CM will go to the differential output, will produce delta V out differential, V out diff. It didn't happen, right? It didn't happen if our resistor was aligned, same. Then if our resistor was same, then the common mode variation will not impact the differential gain. But now, because of the mismatch, the common mode variation will impact the differential gain. This is not good, right? So we don't want mismatch. Second case, when GM1 and GM2 are not the same, it requires some complicated calculation. So what we do is M1 and RSS GM2 1 over GM2, right? Because this impedance would be 1 over GM2. So we'll calculate this. V in over Vx is minus RD over GM1 plus, because this is degeneration, RSS parallel GM21. So this will be minus RD and then if we just make it neat, then it will be this and minus RD. Similarly, if we do a Vy over Vin, then this will be this. So with these two, x minus Vy would be minus RD 1 plus GM2 RSS and minus GM1 times RD. So this turns out delta GM and RD. So let's write it like this: RD and then delta GM. So that's a common source, common mode gain. Well, let's just say it absolute number. I mean the magnitude. So this is our result. What it says is, if we have a GM mismatch, then the common mode. Oh, this is not common mode gain actually. This would be the common mode to differential mode gain. So this is not good, right? If we have a GM1 and GM2 mismatch, then if we change V in common mode, then the common mode difference will be reflected to differential mode. Well, we've discussed the common mode rejection ratio here, which is CMRR. Is a widely used figure of merits. So CMRR, most common form is the gain of differential mode over gain of common mode. So what we want is, we want differential mode gain is large, and then differential common mode, the common mode gain is small. So we like our CMRR large. So here, the common mode rejection ratio, and then these numbers are like dB, 70 or 90. And the other figure of merit is PSRR. PSRR, which is here, supply voltage rejection ratio. This is the gain differential over the gain power supply. So it's when VDD, we apply a VDD some excitation, then we want to see how much of the fluctuation we'll see the V out. So again, we want this value large because we want the differential mode gain large, and then the gain from power supply to the output small. Next, we will briefly look at the offset, input offset. So ideally, if V in 1 and V in 2 is equal, then what we want is V out 1 and V out 2 is equal, right? So, but this is not true. Not true in reality, because like mismatch, right? Because of mismatch, like RD1 and RD2 are not the same, and GM1 and GM2 are not the same, and then VTH1 and VTH2 are not the same, or lots of other reasons that happens all the time. So we define input offset where the input difference voltage causes Vout1 equal Vout2. So ideally we have to give V in 1 and V in 2 are the same, then Vout and Vout2 are the same, right? But what we define input offset is find the V in 1 like star, and then V in 2 star. That makes the voltage output same, and then we call input offset as V in 1 star minus V in 2 star. So that's the input offset. Like the value can be like 10 millivolts, this order. So this is the end of today's lecture. Motivation of the differential pair is reject common mode noise, like such as the interference from the outside or supply noise. And also we haven't covered it, but it's also good for linearity. And we also learned about basics of differential pair, which is common source amplifier. And we also learned that we need a current source here to define the operation of MOSFET M1 and M2 well, and it's independent of V in CM. So we need this ISS to make the circuit independent from V in CM, and this is Vout1 and Vout2. And then we do some equation analysis of these two, and then our gain is differential gain. AV differential mode is minus GM RD. Here's RD. And we also see the common mode response, that what would happen if we change the common mode of this input, and then if you have mismatch, then that common mode difference, common mode variation will translate it to differential variation, which is not good. And we also briefly learned about offset.